assistance and cooperation.
Tell me this, being a pilot on Concorde, were you treated as somehow something different? A cut above the rest almost. I mean, or that maybe other pilots felt a little chippiness because to fly that beautiful thing.
It wasn't us that were a cut above the rest. It was that aeroplane that was a cut above the rest. All we were the privileged pilots and flight engineers who were allowed to operate that aeroplane.
In October 2003, a sleek white Delta Wing Icon touched down in London for the very last time, officially marking the death of supersonic commercial flight. When British Airways and Air France retired the Concorde, it felt like human civilization had taken a collective step backward in technological evolution. For over 20 years, commercial flight speeds have remained completely stagnant. But right now, inside a high-tech manufacturing facility in Greensboro, North Carolina, a venture-backed aerospace startup is building a full-scale assault on the traditional laws of airline flight. Boom Supersonic is finalizing the production infrastructure for the Overture, a next-generation airliner engineered to fly at twice the speed of sound. While traditional industry cynics spent years dismissing the project as a highly speculative venture capital vanity project, the global airline establishment has officially thrown massive financial weight behind the resurrection of speed. Major network giants United Airlines and American Airlines have already poured millions in non-refundable cash deposits onto Boom's order books, locking down early delivery slots for a combined fleet of up to 130 supersonic aircraft. Legacy carriers are betting billions that the luxury travel market is ready to abandon traditional wide-body cabins in exchange for cutting transoceanic flight times completely in half. To understand why this supersonic comeback is a highly dangerous economic gamble, we have to look past the beautiful marketing brochures and analyze the brutal geopolitical limitations of speed. Since 1973, the Federal Aviation Administration has enforced a strict, unyielding overland embargo that completely bans civil aircraft from breaking the sound barrier over land. This means Boom's Overture cannot fly at its maximum speed of Mach 1.7 over the continental United States or Europe. The plane is structurally restricted to executing its supersonic sprints exclusively over open oceans, turning a global transport asset into a highly specialized, niche transoceanic tool. Today, we are opening the industrial spreadsheets to expose the hidden mechanics behind the new supersonic race. How does a startup engineer a massive turbofan engine entirely from scratch when the world's elite engine cartels refuse to help them? How do the unit economics of a narrow, single-class cabin mathematically compete with a giant, multi-tiered legacy widebody? And why is the survival of this entire project riding on a specialized manufacturing facility in North Carolina? Let's break it down. The graveyard of advanced aerospace engineering is littered with conceptual aircraft that failed because they couldn't secure a reliable engine. When Boom Supersonic first went to the global propulsion establishment seeking a partner, they hit an absolute brick wall. The big three legacy engine cartels, General Electric, Rolls-Royce, and Pratt & Whitney, all looked at the spreadsheets, evaluated the massive development costs against the niche supersonic market size, and officially refused to build the engine. Boom found itself completely stranded with an orphan airframe. To survive this industrial lockout, Boom executed a radical corporate pivot. They decided to design their own engine from scratch, establishing a proprietary propulsion program known as Symphony. By partnering with specialist engineering firms like Florida Turbine Technologies and GE Additive, Boom is using advanced 3D printing technology to bypass traditional casting delays. The Symphony engine is engineered to deliver 35,000 pounds of thrust without utilizing high-temperature afterburners. This medium bypass design achieves a critical operational goal, keeping maintenance cycles identical to standard commercial jets while running exclusively on 100% sustainable aviation fuel to clear strict modern carbon caps. The fatal mistake that ultimately bankrupted the Concorde was its completely broken cabin economic model. The Concorde carried 100 passengers in tiny, cramped seats, charging predatory prices that only a microscopic fraction of elite travelers could afford. Boom's Overture is engineering an entirely different revenue strategy. The aircraft is designed with a narrow, hyper-optimized cabin, seating between 64 and 80 passengers. Crucially, it completely eliminates the traditional economy section. Every single seat on the Overture is a standalone, window-facing premium business class suite. By focusing exclusively on the high-margin business traveler, Boom aligns the aircraft directly with the most profitable segment of modern aviation. But the true mathematical core of their business model relies on a concept known as asset velocity. Because the Overture flies at Mach 1.7, it can execute an intercontinental round-trip flight in half the time of a traditional wide-body. A single supersonic jet can cross the Atlantic, drop off passengers, fly back, and log 2.5 times the number of daily flights as a standard Boeing or Airbus jet. This extreme utilization multiplier allows airlines to extract massive amounts of premium seat-mile revenue out of a tiny, hyper-focused fleet of hulls. To prove to skeptical airline boards and Wall Street financiers that they can actually transition from digital renders to serial aircraft manufacturing, Boom has shifted away from computational prototyping and began creating hard industrial facts on the ground. The company officially completed construction on its massive Overture superfactory in Greensboro, North Carolina. Sprawling across a massive 600-acre campus at Piedmont Triad International Airport, this industrial complex is engineered to scale serial production to 33 supersonic airframes per year. The Greensboro superfactory is built to handle advanced carbon fiber composite manufacturing. When an aircraft travels at Mach 1.7, friction with the atmosphere generates extreme thermal stress, heating the external fuselage skin up to 250 degrees Fahrenheit. Traditional aluminum airframes expand and contract under these thermal loads, causing severe structural fatigue over time. By utilizing advanced carbon composites that maintain their tensile strength under high heat, Boom creates an incredibly lightweight, stable, single-piece structure that drastically lowers structural maintenance overhead, clearing a primary barrier that plagued the Concorde. The technical and financial verdict is absolute. Boom Supersonic's Overture program is a high-stakes, masterfully calculated subversion of standard commercial aviation trends. While Boeing and Airbus have completely frozen clean sheet developments to focus entirely on clearing their massive backlogs, this nimble startup is banking entirely on a multi-billion-dollar market demand for premium asset velocity. By taking absolute control of their own propulsion systems, constructing a dedicated advanced composite manufacturing footprint, and focusing entirely on high-margin transoceanic corridors, Boom is engineering a realistic path to bring back the sound barrier. The upcoming rollouts and high-stakes 2027 flight validation trials will determine if the aviation sector enters a revolutionary new era of premium speed, or if the dream of commercial supersonic flight runs completely out of runway all over again.